So yesterday we covered the topic of bias variance related with the underfitting and overfitting, and also the bias variance trade-off. So overfitting, that we have covered the topic, this definition. Okay. So this regularization is related with this overfitting. It's a regularization, as the name suggests, to regularize something. If something is more than the desired value, okay, so that we can minimize through this regularization. So more than the desired one means that is overfitting. So regularization is a technique to overcome the problem of this overfitting. So this regularization, little bit we had discussed this regularization in the last session. So there are two methods, two technique. One is a ridge regularization and another one is a lasso regularization. Okay, so first you have to understand how this regularization is, how we can overcome the overfitting through regularization. Okay, so as already that we had discussed, let me repeat one more time. So y is equal to mx plus my b. So this is the equation of a line. It's a regression line, or you can say it's a best fit line. Okay. So let's say it's a regression line, this one. Now overfitting, what is the overfitting? Overfitting means bias is low. Overfitting means low bias and high variance. And high variance. So the point is, low bias means my model is perfectly fit on the training data. Okay, means the model is working very well on the training data, but the moment you change the data, then it will not behave as good as before. Okay, so this is the overfitting. So now you see this y is equal to mx plus mb. So here x is the input variable and y that is output. So x that is an independent variable, y that is a dependent variable, where m and b, these are the two parameters. So we need to find the optimal value of m and b, okay, so that we can find the best fit line. The best fit line means the line that pass through close to all the data point. So now x, this one is a x. So let's say this x value is very high. This one is x is very high. So if x is very high, the impact of this x on the output, that will be more. Okay, the impact of this x on this output is more if x is high. Sorry, my bad, not x, this m. If m is high, okay, because x is the input, so we cannot change the input. Okay, let x is equal to 2, that is the input. So if my m is, let's say for example, is 100, so that is y is equal to 100 multiplied by 2. Let's say b value is, compared to this m, let is small, let's say 5. Okay, so in this case, if m value is very high, the impact of this term means this term is more dominate compared to this one. Okay, so now the impact of this input, that is more on the output. In other case, if m value is low, or this m value that is less as compared to this, the previous one, m is high, so let's say that is m, that is, let's say 5. Okay, so in this case, the impact of this input on the output, that is less. Okay, so if m is high, the impact of input on y, that will be more, means my model that will capture the pattern of the training data. That is the meaning. Clear? If M is high. So meaning is if M is high, so my model means this model, regression model, that will capture the pattern of the training data. My model that work very well on the training data, because this term that is more dominating compared to this one, if M is high. So if M is low, then uh, my model is unable to fit on the training data. Okay, so that is underfitting. That is underfitting. So M is high, overfitting, M is low, that is underfitting. So now the point is how we can overcome this issue of overfitting through this regularization. Okay, what it does. So regularization is, now we add one penalty term. Okay, we add some extra information. We add some penalty term to just overcome the overfitting. Penalty term means that is this one is a loss function. Okay, so loss function in case of regression is mean square error. Okay, so the yi minus में yi cap and square of this one, that is I, that is 1 to n. This is my loss function. So in this loss function, I add one penalty term. So that is lambda of this w, or you can say that is m. Okay, this is m square. This one is m square. So this m square means that is in case of ridge regularization. Okay, that is norm 2. This one is norm 2. So m square means that is lambda if suppose multiple input feature that we have. So m1 square plus m2 square plus and so on. So m1 that is a kind of uh, parameter. Okay, m2 again that is a second parameter. So likewise m1, m2, m3 means these are the weight. Ultimately these are the weight. Clear? So now this is the kind of relation between this overfitting and how we can overcome this overfitting through regularization. So now ultimately we have to reduce this m value. We have to reduce this m value. That is my ultimate goal. So how we can achieve this m means the low value of this m through this regularization. So this is the extra term. This is the penalty. Okay, so that we add just to overcome the this problem of this overfitting. So in the last class, I derived one relation, the mathematical expression of this m, and the relation, this expression is that is sum of yi minus में y bar xi minus में x bar, where I that is 1 to n divided by this summation xi minus में x bar plus lambda, and where I is equal to 1 to n. Okay, so this is in case of the raise regularization. This already I derived in the last session. So raise regularization. Clear? And this lambda that is a hyperparameter. And the range of this lambda that is from 0 to infinity. Okay. It can never be the negative value. This lambda that is a hyperparameter. And we have to tune this lambda. Okay. So now you see without regularization, this lambda that is not there in the formula of m, and this one is a with regularization, this lambda term is there, means this lambda plus lambda is there in the denominator. So now if you increase the lambda, the m value is decreases. M value that is decreases. Clear? And that is our objective. So now I got this less value, low value of this m if I increase this lambda, where lambda that is a hyperparameter, that is in case of Ries regularization. Okay. So now up to so far, if you have any doubt related to this Ries regularization, because this formula that already that we derived, so now I don't want to waste now time. So now if you have any problem, any doubt in this, just you please ask. So this Ries regularization, this is in case of the linear regression, or I should say the simple linear regression. Simple linear regression. Simple linear regression means, what is the meaning of simple linear regression? Simple linear regression means that is single input and single output. Single input and single output. If suppose if we have multiple input is given, then the multiple linear regression. So in case of the multiple linear regression, now can you tell me the expression or the formula to calculate this I? M, where this m that is only single one, that is a in case of linear regression, simple linear regression. Okay, in this beta I, that is the beta 1, beta 2, beta 3, that is multiple linear regression. So now can you tell me the formula of this multiple linear regression of this beta I? So beta I and m, these are the weights. Okay, these are the beta I. So now we already derived the formula of this beta I, that is x trans inverse x transpose y. Correct. So now this one is without regularization. This one is without regularization. And if suppose this lambda is not there, then this one is without regularization. This m. Okay. So now with the regularization, this beta I that will change by this extra term. So x transpose x plus lambda into my I inverse of this whole, that is x transpose y. This one is with regularization. Okay. So this already that we derived this one beta I. So now I'm giving to you this as an assignment. Just you please solve and just you derive the formula of this beta I in case of regularization, with regularization. Okay, this I already derived this one. So in case of multiple linear regression, okay, you will get this x transpose x in place of this single one, x transpose x plus my lambda I inverse of x transpose. Okay, so now there are some understanding of this related to this Ries regularization. The first point is how the coefficient that get affected. Okay, how the coefficient means this beta. Okay, means how the coefficient that get affected when we use the regularization. So how the coefficient get affected, that is a beta. Okay, so let's say for example beta 1 is 5000, let's say for example, and beta 2 that is let's say 500, and beta 3 let's say that is a 50. Okay, for example, clear. Now this is the case of without regularization. Without regularization. Now if you use this regularization, this means if you use the one this extra added term, this lambda. So now you see the impact of this lambda on this beta I. So this as you increase the lambda value, this beta I, okay, this beta 1, beta 2, beta 3 means that is beta I that is going to reduce. Okay, but now you see this higher value of beta are impacted more. Is beta 1 that maybe after this lambda, after this regularization, this beta 1 that, maybe this uh, see 300, beta 2 let's say 30, and beta 3 let's say 10. Okay, so now you see beta 3 change from this 50 to 10. Now this 500 to 30. Now you see here 5,000, from this 5,000 to 300. So now higher value are impacted more. Higher value of beta I are impacted more. Impacted more. And that's what why I want. Okay, higher value that is are impacted more. Clear? So that is a first understanding with respect to this res regularization. Now second, as you increase the value of this lambda, this beta I or this m that will decrease, but not equal to 0. But not equal to 0. So now you see the formula of this m, this one. If you increase the lambda, that m that will not be equal to 0. Okay. You put for an example lambda is 10,000 or that is 10 lakh. 10 into 10 to the power 4, that is 1 lakh. Okay, in that case, you will never get this m value that is equal to 0. Clear? So that is a second point of understanding of this res regularization. Clear? So this lambda, if you increase the lambda, that m that value be decreases but never be equal to 0. Now third, this bias variance trade-off. Now this overfitting is what? Overfitting means that is bias is low and variance that is high. Variance high. But this after this regularization, okay, so variance that will be low. Bias high. Clear? So if you apply this lambda, this regularization, the variance that is decreases and bias that is increases, because this m value that is less. Clear? So now the fourth understanding of this regularization is impact on the loss function. That is impact on loss function. So now you see this is my graph in between this loss and this m. and this one is a convex function. Okay, and here that is L, that is, sorry, lambda value is 0. So now if you increase the value of lambda, this say lambda is equal to 1. Now if you increase further this lambda, then say lambda is equal to 5. Then here this one is, say lambda is equal to 10. Okay, so here minima of this m, earlier it was here at the value of this lambda is equal to 0. Okay, the minima. So here minima of this m that has shifted towards to the left. So here this lambda is equal to 10. So now minima that is shifted towards this low value of this m. So this is m star. So if you increase the lambda, that m that is decreases, so we can cross verify by this graph also. Okay, so that is the impact on the this loss function. So minima of loss function that will occur at lower value of m. Minima of loss function will occur at lower value of m. Clear? So this is all about the ridge regularization. So now next, that is the lasso regularization. So lasso regularization, that is loss function is, that is sum of summation of yi minus yi cap and square of this one where I that is 1 to n. Okay, so lasso regularization, that is norm 1. So that is lambda into me, that is m. This one norm m, norm 1. Okay, so let's say in case of multiple linear regression, so this m, this one that will be m1 mode plus m2 mode plus m3 mode and so on. Clear? So in case of simple linear regression, this lambda into my mode of m, that is norm 1, norm 1. So this is the penalty term, this is the extra term that we are adding in the lasso regularization just to overcome the effect of overfitting. So again that we do the same way, this differentiation of this L. Now I derive the formula of this M in case of lasso regularization. Okay, so now differentiation of this L with respect to this M. Okay, so intentionally just I am just putting here 2. Okay, that it will not affect on this loss function. Okay, so here intentionally I multiply by 2. So now if you do the differentiation, so that is, see, first before just doing this differentiation, let me just simplify this equation one more time. So that is summation of I is equal to 1 to n yi minus may yi cap, that is m of x I minus may b. Okay, and this square plus may 2 lambda into my m, and this summation that is I is equal to 1 to n yi minus may m x I minus may this plus m x bar and square. Okay, this already that we know that b is equal to y bar minus my m x bar plus my 2 lambda m, that is as such. Clear? So up to so far, any doubt? This is my L. Okay, is there any doubt? Okay, fine. So now differentiation of this loss function with respect to this M. So twice of this summation I is equal to 1 to n yi minus में mx I minus m y bar plus में mx bar, where y bar and mx this y bar and x bar, that is the mean of this output, and this x xi plus x bar plus 2 of this lambda. Clear? So now in the next one, that is differentiation left hand side. So see 2 yi minus में mxi to this summation yi minus में mxi minus में y bar minus में y bar plus में mx bar plus में mx bar. So I rewrite again this equation here, minus xi plus x bar plus 2 of lambda. Okay, correct. So now here this 2, this summation I is equal to 1 to n, this yi minus में m sorry yi minus में y bar and minus m just common xi minus में x bar. Okay, and xi minus में x bar, just take the negative sign common, and plus में twice of this lambda. Okay, so now this minus में 2, this summation of I is equal to 1 to n yi minus में y bar. Okay, this one xi minus में x bar plus twice of m summation of I is equal to 1 to n xi minus में x bar whole square plus में twice of lambda. Now we will put this equation that is equal to 0. Okay, so now 2 this cancel out throughout. So now this formula of this m, that will be summation I is equal to 1 to n yi minus में y bar xi minus में x bar minus में lambda divided by xi minus में x bar and square of this one, where I is equal to 1 to n. Now you see the difference of this m formula and compare with this ridge regularization. So let me write here, this is the ridge and this one is a lasso. So in the ridge, m is, that is summation yi minus में yi bar xi minus में x bar. Okay, where I is equal to 1 to n xi minus में x bar summation I is equal to 1 to n plus lambda. Okay, and here that is m summation yi minus में y bar xi minus में x bar I is equal to 1 to n minus में lambda summation xi minus में x bar whole square I is equal to 1 to n. Clear? So this is the case of ridge regularization and this is the case of lasso regularization. So now you tell me, here I do one mistake. in this derivation. So now can you please tell me where is the mistake? In which step that I have done wrong? This L is this one. Okay, and differentiation of this L with respect to M is this one. So here I did one mistake. So now can you please tell me where is the mistake? In which part? This is the first term and this one is the second term. Hello? Let me check in the chat box. Is my voice audible? Okay, fine. Okay, so the mistake here is this mode M. This mode M is not differentiable. This mode, actually mode is not differentiable. So how we can differentiate this expression with respect to M, and how I can write this 2 lambda, because this one is different, this mode is there, here mode is there, this one mode. Yes. So at M is equal to 0, this is not differentiable at M is equal to 0. Okay. So now this is the case where this M is positive. Okay. And the formula that will become this summation yi minus y star xi minus x star plus lambda sum of this xi minus x star square I is equal to 1 to n in case of this m less than 0. In case of m less than 0, so this will be plus, m greater than 0, this will be minus. Okay, and at m is equal to 0, so m is equal to this one, means that is no, means regularization, means there is no regularization, nothing is there. Okay, so this m that is greater than 0 and m that is less than 0. Clear? So now first we understand these two expression. Okay, the intuition of this m in case of lasso regularization. So here one thing is there. So see, if you increase the lambda, see here m that will never get 0. Okay, this m that will never be equal to 0, but see here, if you increase the lambda, this m that will be equal to 0 on some particular value of this lambda, maybe. Okay, okay, here this m that is negative, so here if you increase the value of this lambda, so that m that will be equal to 0, so there is a, so this is the first difference between the ris and lasso regularization. So difference is here that m that will never be equal to 0, here this m that is equal to 0 if you increase the value of lambda. Lambda that cannot be negative. Lambda that cannot be negative. So if you increase the lambda here, in both the case, this ris and lasso, ris that is m that is not equal to 0. Okay, correct. Now you see the second point in this lasso regularization. So let me explain here. So see, this one is a suppose this expression that is first, and this one is, let's say, second one. Okay, so let's say in first expression, so m is positive. So when you will get m positive, so this lambda, that is a hyperparameter. Lambda, that is a hyperparameter. So this is the penalty that we are adding. Okay. So now see here, this uh, yes, this one. So this is the kind of the penalty that we are adding, and this lambda value, that is never be equal to negative, never be the negative value. Okay. So this is a hyperparameter. Only this value that is positive, m, that is square and positive, this will be positive, and this positive. Then only this we can add some extra information. Gitanjali ma'am, is it clear to you? Means actually the regularization means we are adding some extra information. So this is positive, this one is positive, then only we can add some extra term. Fine. So now here, okay. So in this first expression, so how do we get this m greater than 0? So let's say this is, let's say, 100. Okay, this lambda as such. Okay, and let's say this one, the denominator part, that is 50, let's say, and this is the formula, that is m. Okay, so now this, let's say lambda is equal to 0. So that is m is 2. Now lambda is equal to 50. So now m is 1. Okay, clear? Now third case, that is lambda is equal to 100. So now here, that is m is 0. So means m value is continuously decreasing if you increase the value of lambda. Correct? Now fourth case, that is first one is lambda is equal to 0, second lambda is equal to 50, third lambda is equal to 100, and fourth, if you still increase the value of this lambda, that is 150. So now here m, that will be -1. Okay, m, that is -1. Here the point is the model that will not give the bad result. The model that will not give the bad result. So the model that will stop here. If lambda is equal to 150, so the model that will not use this expression, first one, the model that will use this one, second expression, because here the m value is negative. Now this point is clear to you? Okay, so now come to this second expression. So how this m value is negative in this one? Let's say this expression, this one is, let's say, this one is, in the next one, m value is -150 plus lambda divided by 50. Okay, clear? That is the second expression. So m negative value. So let's say lambda is equal to 0. So m is -3. Lambda is equal to 50. Then m value is -2. Lambda is equal to 100. Okay, the m value, that is -1. Lambda is equal to 150. The m value, that will be 0. If you increase still the value of lambda, let's say 200, the m value, that will be +1. Okay, so now in this case, the m value is positive. Okay, means here, that is m, that is -3, means m value -3 means that is a slope, that is -3. So let's say this one is -3, -2, this one is a -2, this one is -1, let's say this one is -1. Now 0, this one is 0. Okay, now m plus 1, so this is plus 1. So now in this case, the model that will not give the bad result. Okay, the model that will stop here. And for this lambda is equal to 200, the model that will use this first expression. Fine. So that is the impact of this lambda on this m in case of the raise regularization, because in lasso that m that will never be equal to 0. So the important point is, now in case of raise, that m that will never be equal to 0, but in case of lasso, maybe the sum of the value of lambda, that m, the value that is equal to 0. So now the question is, where we use this raise regularization and where we use this lasso regularization. So raise regularization. So raise regularization, just you apply the raise regularization in this case, in the case where you don't want to lose the feature. Okay, and all the features are important. If suppose all the features, if you know the data very well, and if you don't want to lose any one of the feature, okay, just you use the raise regularization, because in that case the m value that will never be equal to 0. M, that is a feature. I means m, that is a this kind of uh, is parameter. Clear? So the lasso regularization, so in lasso, suppose if you want some of the features are not important for the model, then you use the lasso regularization. Okay, so in that case, just you use a lasso regularization. Maybe some of the beta that will equal to 0. So if you know the data set, okay, and if you know some of the input features are not important, not so important, then you use the lasso regularization. And the third case, if you don't know the which one of the input features are important, okay, so in that case, just you use the elastic net regularization. Elastic net regularization. So if we have very large data set and we don't know which features are important, okay, so which one should we use? So RIS or lasso, then you use the elastic net regularization. This one is a combination of RIS and lasso regularization. So elastic net regularization is a combination of RIS and lasso regularization. So here this L loss function is yi minus yi cap and square of this one I1 to n plus a w square plus b this w. Okay, so this one is the RIS, this one is a lasso. So now this is the loss function in case of elastic net regularization. This is the loss function. So this one is the loss function in case of simple linear regression. So in case of regularization, So this is the loss function. So now here the lambda is a plus b. Lambda is a plus b. And there is one more parameter, that is L1 ratio. L1 ratio. So L1 ratio is a divided by a plus b. So these two are the hyperparameter in case of this elastic net regularization. Okay. So where this L1 ratio, this a divided by lambda, and a, that is lambda 1, this L1 into my lambda, or b, that is lambda minus may this b. So by default, the value of this lambda, that is equal to 1, and this L1 ratio, by default the value of this L1 ratio is 0.5 by default. So the meaning is, if L1 ratio is 0.9, let's say if L1 ratio is 0.9, okay, so L1 ratio is 0.9, that is L, that is 0.1, so means 90% is regularization and 10% is lesser regularization. Clear? If L1 ratio is, let's say 0.7, then 70% is ris regularization and 30% lesser regularization. So here this L1, this ratio, and this lambda, so both are this hyperparameter in case of elastic net regularization. Okay. So now there is a case number 1 and case number 2. If we have the input data set is, let's say, multi-collinear. If our input means, if our data set is multi-collinear, means x1 and x2 means are dependent on each other, x1 and x2 that are dependent on each other. So in this case, we should use the elastic net regularization. Let's say weight and height. Okay, so weight, that is x1, and height, that is x2. Okay, in some of the data sets, suppose x1, that is a weight, and x2, that is a height, these two input feature. So here x1 and x2 both are dependent, both are related to each other. If weight increases, the height, that will also be increased. Okay, if weight is less, the height, that will be less, means dependent on each other. So in this data set, better to apply the elastic net regularization. So there are two cases. First case is where we don't know which one of the input features are important, and the second case, if the features are linearly dependent on each other. So in these two cases, that you should apply the elastic net. Res regularization, if you don't want to lose any input feature, then better to use the res regularization. If you know your features are not so important, some of the input features are not so important, then you use the lesser regularization. So I hope this everything related to the regularization is clear to all of you. So if you have any doubt, then you please ask here in the chat box. So let me again revise the whole lecture. This regularization is actually we are adding extra term, or we are just adding a penalty term. This is the penalty term in case of the res regularization. Ridge regularization means that is a L2 norm. Lasso regularization means that is a L1 norm. Okay, means L1 norm and L2 norm means I am talking about this penalty term. So in case of this in case of ridge regularization, this lambda that is coming in the denominator. Okay, and in case of ridge regularization, this lambda that is coming numerator side, this one. Okay, so this one is a ridge, this one is a lasso. So now if you increase the lambda, that m that will never be equal to 0, and here if you increase the lambda, that sum of the value at this lambda, sum of the this at instant this lambda, you will get this m is equal to 0. And this is the kind of intuition, this if suppose m that is negative, and if somehow we achieve this m positive, then the model that will not give the bad result, it will switch to the next another expression. Okay, and this one is the impact of this understanding of this ridge regularization and also that lasso regularization. So now question is, how do we know from the data if the dependency is linear, dependence is linear? So in case of non-linear dependency, is there any regularization? Means yes, dependency means you can just check uh, by the curve fitting also, or you can check with the data visualization. Okay, data visualization. So overfitting is not a desired thing. So overfitting that may occur, just you check uh, uh, if suppose your uh, model that perfectly fine on the training data, and if suppose it it not behave um, perform it does not perform well on the test data, then that is a overfitting. Okay, you can just check the data visualization, means after applying uh, uh, this algorithm. Okay, let's say linear regression or logistic regression or decision tree or whatever the X algorithm. Okay, so just you check uh, this overfitting this. If your model uh, perfectly fit on the training data, then it's overfitting. So just you have to play around with this hyperparameter. Okay, so this is a some point this related to the ridge regularization. There's an impact on loss function and this overfitting, how to overcome this overfitting uh, with this regularization. And this lambda, if you increase the value of lambda, that m that will never be equal to 0 in case of ridge, but in case of lasso, that m that will be equal to 0 in some of the case of this lambda. So now impact on loss function, this minima of this loss function that will occur at the lower side, lower value of m. Yes. So now if you have any doubt in any one of the slide, now you please ask your question in the chat box. Okay, so perfectly fine. If you don't have any doubt, then we can wind up the session here. So thank you all for listening the lecture. So tomorrow that we'll be having 4 session. Okay. So now I request you to uh, please do your assignment, this quiz, and please score more than 40% marks for the certification. So if you have any doubt related to your quiz, please you ask here. So you will be having 1 hour to solve this quiz question, and 1 hour you can just choose as per your convenience. Any 1 hour. Okay. Okay, fine. So now I'm going to just wind up this session. So tomorrow we will meet again at sharp 10 o'clock. So thank you very much. Okay, take care. Bye.